Alright, so here's going to be our population model example. This is the information that they're going to give you in a problem, and they're going to say something like assume exponential growth. So right away we're going to have to write an exponential growth function in order to solve this problem. The question is asking, when will the population, this is of San Jose, California, when will the population of San Jose, California surpass 1 million people? 1 million, so remember that's 1 with 6 zeros after it. So we're kind of getting close here, but really not sure, but it's an exponential growth. So, 1 million people. First, what we need to do is figure out an exponential growth function. How do we do that? Well, we know that our exponential growth is going to look something like f of x is equal to a times b to the x. We know that we're using time, so years is going to be our actual input function, so I'm going to change this now to f of t for time equals a times b to the t. And remember that a is always our initial value. A is the initial value. So I'm going to rewrite this now as f of t equals p sub 0. So population sub 0, which is the initial population, times b to the t. And now you don't always have to show me all of these steps. If you could go right here from now on for population examples, that's fine. I just wanted to show you why we're using this notation. So again, this is our initial value. This is our growth factor. And in time, t years. We know that PO is the initial value. And if I'm looking at from 2000 to 2007, this is the only information they give us. So our initial population is this number right here. So now I can rewrite this into my function. F of t equals the initial population 898,759 times b to the t. Once I have this information, I can figure out what my exponential function is going to be using the other piece of information that they give us in 2007. Well, in 2007, what's the t value going to be? It's been 7 years, so our t value is going to be 7. F of 7 equals 898,759 times b to the 7. Well, I know what my f of 7 value is because they gave us that information. So now I can again rewrite this as, I'm going to try and write small here, 939,899 is equal to 898,759 times b to the 7th. And now I'm solving for b. I'm trying to find what my growth factor is so I can write an exponential growth function. Just like you would normally do, we're going to divide both sides by the 898 number. 898,759. And I'm just going to change colors here so we don't get confused. That new number now is we're going to have approximate b to the 7th is approximately equal to 1.0457. And that number is kind of long. I would just leave it in your calculator. Then what we're actually going to do is take the 7th root of both sides, right? Not the square root because we're raising it to the 7th power, so we're taking the 7th root of both sides. B is equal to the 7th root of 1.0457 ... whatever. How do I take the 7th root on my calculator? Well, there are two ways. One way that the calculator can do it for you is, I'll show you in class, it's using the button that has an X for that square root. Otherwise, we know this is the same thing as, this is actually equal to raising this number, 1.0457, raising this number to the 1/7. They mean the same thing. So if you do that on your calculator, you're going to get b is approximately, I should use squiggle lines, b is approximately equal to 1.0064. But are we done with the problem? Of course not. So, we have to rewrite. P sub t, or I used f of t before, I'm changing population over time, is the same as 898,759 times our b value raised to the t. What did the question ask? It asked when the population is going to reach 1 million. So am I substituting 1 million in for t? No, because t is time. I want to know when the population is going to be 1 million. So I'm solving for t. So here, I'm going to put in 1 million. And that's equal to this function. And we're going to talk about how we can actually algebraically solve this equation, but for right now we're going to use graphing. So on your graphing calculator, you're going to input in y equals 1, or y1 you're going to put equals 898,759 times 1.0064 to the x, which we know is really to the t. And then in y sub 2, you're going to put in 1 million. You're going to end up getting a graph. Remember, 1 million is a constant, so that's going to be a straight line. And it's going to look something like that. How do we find what our t value is? Our t value, which is really our x in this case, is the intersection of both of those graphs. So whatever this point is here. We know that the y value is 1 million because that's what we wanted. We want to find out what our x value is, or what our t value is, how many years. So you're going to do on your calculator, second calculate, scroll down to intersect, push enter when it's on the first curve, push enter when the cursor is on the second curve, push enter for a guess, and hopefully you get 16.73 for your x value and 1 million for your y value. That means that t is equal to 16.73. Well, what does that mean? That means that the population will surpass 1 million people 16.73 years after the year 2000. So, sometime in 2016, the population of San Jose, California will surpass 1 million people. And that's how you do a population problem like that. Another population problem that you might get is a little bit easier. This time it's going to use a logistic function. It's going to ask you to find the population for t years after 1990. So again, it's going to ask you, when is the population going to reach 1 million people? And this time they give you the function. It's a logistic function. When will the population reach 1 million? So again, you're going to graph this on your graphing calculator in y1. In y2, you're going to graph 1 million. So you're going to get a graph that looks something like this. Because remember, our carrying capacity here is our C value, which is about 1.3 million. But I want to know when it's going to be equal to 1 million. So your calculator is going to look something like this. You're going to find the intersection here, and hopefully you find the intersection to be 84.51 for your x value, and of course we want 1 million to be our y value. So that means that about 84 and a half years after 1990 is going to be when the population surpasses 1 million people. So 84 and a half years after 1990 is approximately midway through 1984 is when the population would pass 1 million people. And that's how you use a logistic function to model populations.